Imagine this. You step outside, and the sunlight feels different, thinner, somehow. The world looks perfectly normal. Birds are singing their usual songs. The distant hum of traffic continues its steady rhythm, but a clock you cannot see has just started ticking. 8 minutes. That's how long it takes for sunlight to travel from the sun to the earth. It's also, fascinatingly, how long it takes for gravity to travel. According to Einstein's theory of general relativity, gravity isn't an instantaneous force. It propagates at the speed of light. So, if the sun were to vanish right now, we wouldn't have any idea for 8 quiet, unsuspecting minutes. This is, of course, a thought experiment. It's a gentle, cinematic walk through the science of what would happen if our stars suddenly disappeared. In the real world of astrophysics, stars don't just blink out of existence. They live for billions of years, and when they do reach the end of their lives, they do so in spectacular, predictable whatever, swelling into red giants or collapsing into dense remnants. But as a way to truly appreciate light, gravity, our climate, the delicate balance of biology, and even our own human resilience, this impossible scenario is a powerful and illuminating lens. Let's use it to explore the intricate connections that bind us to our star. So, for those first 8 minutes, everything holds. The world continues, as it always has. The Earth, held in its familiar path, continues to orbit an empty point in space where the sun used to be. The moon, our silent companion, still rides its slow, graceful circle around us. Bathed in sunlight that is, for now, still arriving. Everything we see, everything we feel, is an echo of a sun that is already gone. Sunlight from the recent past keeps arriving, like a final message sent across the vastness of space. Think of it this way. Photons, the tiny, individual packets of light energy, left the surface of the sun over 490 seconds ago. They were already on their journey, racing toward us at the ultimate speed limit of the universe. They have no idea that their source is no longer there. The same is true for gravity. The ripples in the fabric of space-time, created by the sun's immense mass, are also moving at the speed of light. These gravitational waves are what tell the Earth how to move, how to curve its path through space. For these 8 minutes, the Earth is still following the gravitational instructions of a sun that has already vanished. On the surface of the planet, life goes on, completely oblivious. A few people might feel a sudden, inexplicable chill and pull their jackets a little tighter. Thinking it's just a passing cloud or a gust of wind, they glance up at the blue sky, see the familiar golden light, and think nothing more of it. But deep underground, in hypersensitive observatories designed to detect the universe's most elusive particles, the first real sign has arrived. Scientists monitoring the constant stream of particles called solar neutrinos would notice something astonishing. The stream has stopped abruptly because neutrinos travel at nearly the speed of light and interact so weakly with matter. Their sudden absence is the very first clue, arriving just over 8 minutes after the event. The first true, undeniable signal that something fundamental has changed. For everyone else, the moment of truth is still seconds away. What happens when the very last photons, the final remnants of an 8-minute-old sunset, finally arrive? What happens when gravity, like a cosmic tide going out, empties from the center of our solar system, releasing its hold on all the planets? In a few breaths, the sky will change forever. The familiar blue will fade to an inky, star-filled black. But that is only the beginning. We are living in a memory. This is not a metaphor, but a simple, staggering fact of physics. The sun you see in the sky, the warmth you feel on your skin, is 8 minutes old. It takes that long for light to travel the 93 million miles from its surface to our eyes. On any normal day, this delay is a scientific curiosity, a fun fact to share. But today, it is a countdown. Today, we are living in the final 8 minutes of an ordinary world, suspended in a pocket of time that has already passed. During these last 8 minutes, nothing appears to be wrong. The world unfolds with the gentle rhythm it always has. The sun glows with its familiar, life-giving brilliance. The shadows of trees and buildings lie precisely where they should for this time of day. Birds continue their songs, unaware that the stage they perform on is about to go dark. The planets visible in the sky, our silent celestial neighbors, keep their stately, predictable pace. Everything feels normal. Everything looks normal. But we are bathed in the last wave of energy that left a star that, in the present moment of the universe, isn't there anymore. We are ghosts, living in the light of a dead star. It's a strange thought that something as fundamental as gravity needs to travel. We think of it as an instantaneous force, the invisible chain that tethers our Earth to the sun. But it isn't. According to Einstein's profound theory of general relativity, gravity is the curvature of space-time itself, and when a massive object like the sun vanishes, it creates ripples in this fabric, much like a stone dropped in a pond. These gravitational waves propagate outward, not instantly, but at the finite, unyielding speed of light. So, the very moment the last photon of sunlight begins its journey to Earth, the last ripple of the sun's gravity does too. For these 8 minutes, Earth continues its graceful arc, held in an orbit by a gravitational field that no longer exists at its source. It's as if we are on a cosmic carousel, still spinning, unaware that the central pillar has already crumbled. The moment the light finally stops, the curve of Earth's path will change. It won't be a sudden jolt or a violent stop. It'll be a gentle unhooking, a quiet release. Earth will simply stop turning its corner and begin to travel in a straight line. A solitary ship cast adrift into the vast, cold darkness of interstellar space. Meanwhile, our world is a thermal ocean, a reservoir of stored energy. For billions of years, the rocks, the vast oceans, and the very air we breathe have been absorbing the sun's relentless energy, holding it in a delicate balance. This planetary warmth is our inheritance. Even when the sunlight finally stops, this stored heat won't vanish instantly. The ground beneath our feet and the deep, dark waters of the sea will begin to radiate that warmth back into the sky. A final, faint blush against the encroaching cold. This process gives us time. Not much, but time. Think of it as a planetary budget. Above us, at the very top of our atmosphere, the Earth used to receive a constant income of 1361 watts of solar energy for every square meter facing the sun. After accounting for reflection from clouds and ice, Earth absorbed, on average, about 240 of those watts across its entire surface. This steady, reliable flow of energy kept our global temperature in a comfortable equilibrium, allowing life to flourish. It was the perfect balance between energy in and energy out. When that input suddenly drops to zero, our balance begins to tilt. The scales tip irrevocably toward cold. Every second that passes, we will be losing more heat than we gain, bleeding our precious warmth into the void. But for now, for these last few moments, we are still walking in daylight. We are blissfully, beautifully unaware. We are existing in the final, fleeting echo of a sunbeam. The sky is blue, the world is bright, and everything feels safe. We are standing on the precipice of an unimaginable change, living out the last seconds of a day that has, in reality, already ended. We are waiting until the universe flips a switch. 8 minutes and 20 seconds. That's how long it takes for the last light from the sun to reach us. After that moment, Passus, something unprecedented happens. No clouds roll in. No eclipse shadow sweeps across the land. The world doesn't slowly darken. Instead, daylight simply fades. It's as if a cosmic dimmer switch has been thrown, instantly plunging our world from bright blue to absolute black. The sun doesn't set. It just vanishes. The familiar azure canopy of our sky, a product of sunlight scattering through our atmosphere, is gone. In its place, you might expect pitch darkness, an impenetrable void. But that's not what you see. As your eyes adjust, you witness a celestial revelation. Stars, once timid and few, begin to snow into view, a silent, glittering cascade. Without the sun's overwhelming glare, the night sky is reborn, revealing a richness and depth you've never experienced. The Milky Way, usually a faint, hazy band, now arcs across the heavens like a brilliant ribbon of frost. Planets that once shone as distinct, Bright points in our twilight are now just other stars in a suddenly crowded tapestry. The moon, our constant companion, no longer glows, without sunlight to reflect. It's a dark, charcoal coin hanging in the silent sky, a ghost of its former self. Down on the surface, a new, artificial dawn begins. Streetlights, governed by photosensors, pop on in unison. Thin, amber light spills across a world that has lost its primary source of illumination. The air itself seems to change. It feels stiller, quieter. The weather, our planet's great atmospheric engine, loses its fuel. The winds, cyclones, and gentle breezes were all powered by the uneven heating of Earth's surface by the sun. Now, as those temperature differences begin to soften and equalize, the air loses its drive. The planet holds its breath. As this new reality unfolds for us on the surface, other, more subtle confirmations are registered. Somewhere, in a high-tech observatory, its gaze locked on the sun. Astronomers watch as its turbulent, rippling face freezes mid-boil, its screen switching from a dynamic star to a static, black circle, and deep underground, shielded from cosmic rays. A sensitive neutrino detector registers the precise moment the stream of ghostly particles from the sun's core ceases. For the scientists, this is the true confirmation. The sun's nuclear heart didn't just stop shining. It truly winked out 8 minutes and 20 seconds ago. And then, a second, more profound change begins. It's not visible, not audible, not something you can feel on your skin, but it is everywhere. It is gravity. For billions of years, our planet has been locked in a delicate dance, tethered to the sun by its immense gravitational pull. Now, that tether has been cut. The Earth's orbit unhooked. We are no longer following a curve. Our path becomes a straight line, a perfect tangent to the orbit we were following just a moment ago. We are now a rogue planet, beginning to slide silently through the cold, empty space where the sun's familiar pull used to be. The planet is now adrift. We are coasting on pure momentum, flying through the solar system and out into the interstellar void. How long will it be until we feel the effects of this cosmic What does our new, untethered path through the galaxy look like? Next time, we'll explore gravity's quiet click and the beginning of our long, cold journey. Gravity doesn't yank us. It guides us. With the sun gone, that guidance simply changes. For months, perhaps even 4 years, you wouldn't sense a thing standing on a street corner. But on a cosmic map, the difference is immediate and profound. We are no longer circling. We are coasting. Imagine you're on a merry-go-round, and suddenly, the central post vanishes. You wouldn't be pulled inward anymore. You'd continue in a straight line, carrying the speed you had at that final moment. That's Earth now. Before, our planet raced around the sun at a blistering 30 kilometers per second, or about 67,000 miles per hour. That's fast enough to cross the United States in just a few minutes. Now, freed from that gravitational loop, we continue at that same incredible speed, but in a straight line. We're like a stone let loose from a sling, heading out into the vast interstellar dark. Our new trajectory is determined by the exact direction Earth was moving at the moment the light ended. A journey into the unknown has begun, silently. But we aren't alone on this journey. The moon remains with us. It orbits Earth, bound not by the sun, but by our own planet's gravity. It's our constant, gray companion in the deepening twilight. The moon still pulls on our oceans, raising tides. They'll be slightly different, of course. Without the sun's additional tidal pull, the overall range between high and low tide will change, becoming a little less extreme. But the familiar, ancient rhythm of the oceans rising and falling will continue in the dark, a gentle pulse pulled only by our loyal satellite. This celestial dance, now a duet instead of a trio, offers a sliver of normalcy in a world forever changed. Elsewhere in the former solar system, the same quiet release is happening. Mercury, Venus, Mars, Jupiter, every planet, asteroid, and comet also slips free from its orbit. What was once an orderly, clockwork system becomes a fountain of silent stones, flung outward on their last known velocities. Each world is now a solitary traveler on its own linear path into the cosmos. It's a startling, almost poetic mental picture a cosmic dispersal, a silent, synchronized exodus. And yet, here on Earth, the night remains calm. There's no shudder through the ground, no cosmic boom, no sound at all to mark this momentous shift. The universe doesn't announce its biggest changes with a fanfare, but with a quiet click. Under our feet, a far slower, more insidious change begins. Without fresh sunlight to warm the ground and the air, the surface of our planet begins, ever so gently, to cool. This isn't a sudden plunge into an ice age. Not right away. The Earth has a tremendous amount of stored heat, a concept known as thermal inertia. The oceans, in particular, are a massive reservoir of warmth, and they will release that heat slowly, acting like a planetary radiator. For a while, this stored energy provides a comforting buffer against the cold of space. But the trend has been set. The balance has been broken. The planet's heat budget is now in deficit, and the slow, inexorable slide toward a colder state has begun. How fast does a planet lose its warmth when its star goes out? Where will the first, most tangible losses be felt? It won't be uniform. Some places, like deserts, will cool much faster than coastal regions buffered by the sea. The atmosphere itself will begin to change, driven by this new thermal gradient. The familiar patterns of wind and weather, all driven by the sun's energy, will start to unravel and reform into something new, something alien. Next, we'll explore the first night's weather. What happens to the air we breathe and the world around us as the long sunset truly begins. The first night is beautiful and unsettling. You look up and notice something missing. There's no soft glow from the west, no hint of a sun just below the horizon. There's no moon, either. It's just a clean, dark dome, punctured by the brilliant pinpricks of stars. Looking down at the Earth from an imaginary vantage point, you'd see city lights carving new continents across the planet, a glittering network of human presence against the profound blackness. The stars themselves seem to pulse, but that's a trick of our atmosphere. It's the last vestiges of our planet's breath. Tiny, invisible ripples of warm and cool air, constantly bending the starlight as it travels down to us. It's a familiar twinkle, a sight that has comforted stargazers for millennia. But as the days pass, even that familiar twinkle begins to fade. The air is calming, the final shivers of a planet settling into a deep, quiet stillness. Wind, as we know it, is a creature of sunlight. The engine of our atmosphere is driven by a simple thermal gradient, warm air rising at the equators, and cool air sinking at the poles. This constant cycle of rising and sinking air creates the jet streams, the trade winds, the weather that defines our world. But now, with the great furnace of the sun turned off, that engine is winding down. The temperature difference between the equator and the poles begins to shrink. As a result, massive weather systems lose their power and weaken. The storm tracks that once marched across oceans and continents falter, then stall completely. The planet's great engine sputters to a halt. The oceans, those vast, warm stores of solar energy, begin to exhale their accumulated heat into the cold of the endless night. It's a slow, gradual process, an unwinding that will take place over days and then weeks. At first, the drop in average global temperatures is gentle, almost unnoticeable, a few degrees over the course of several days. The immense thermal inertia of the oceans acts as a buffer, keeping coastal regions relatively less cold. But inland, away from the moderating influence of the sea, the change is more rapid. Deserts, which once baked under the sun and cooled dramatically at night, now only cooled. High mountain peaks, exposed and far from the warmth of the sea, begin to chill quickly under the clear, endless night sky. The clouds, which once dotted our skies, begin to thin, with less solar energy to drive evaporation from the oceans, and weaker convection to lift that moisture into the air. The water cycle grinds to a near stop. The sky grows clearer, a perfect, crystalline black. But this clarity comes at a cost. With no cloud blanket to trap warmth, the remaining heat from the Earth's surface leaks away even faster, radiating unimpeded into the frozen vacuum of space. Far above, other familiar lights begin to fade. The auroras, the beautiful northern and southern lights, flicker and die. They were a direct result of the solar wind, a stream of charged particles from the sun interacting with our planet's magnetic field. Without that constant wind, our magnetosphere falls quiet. The celestial light show is over. Higher still, in orbit, thousands of satellites fall into a strange twilight of their own. Their solar panels, designed to drink in sunlight, go dark. For those with batteries or small onboard reactors, these become precious lifelines, their only source of power in the permanent eclipse. They are silent sentinels, orbiting a world that is slowly, inexorably, going dark and cold. And down on the surface, beneath the clear, star-filled, and increasingly frigid sky, a single question begins to grow sharper in the minds of everyone. It starts as a whisper, a distant concern, but with each passing hour of the unending night, it becomes more urgent, more oppressing. At what point does this creeping cold transition from an inconvenience, from a simple change in the weather, to a fundamental question of survival? How long do we have? The answer depends entirely on one thing: the rate at which our world cools. In the quiet aftermath, there's a strange comfort to be found in the numbers. They offer a predictable, ordered path into the coming cold. Within just 1 week, liberated from the sun's constant warmth, Earth's average surface temperature would begin its descent, slipping toward freezing and then past it. Depending on where you are on the planet and the season you left behind, the global average would settle around a biting -17°C. That's a cold familiar to some parts of our world, but a devastating shock to the whole. After a full year of this relentless twilight, the global average temperature might plunge to near -73°C. This is a punishing, alien cold, the kind of deep freeze found on other worlds, not our own. Why this drastic, inexorable slide? The answer lies in a simple, cosmic balance. Our planet, like any warm object in the vacuum of space, constantly radiates its heat away. It glows, not in visible light, but in the infrared spectrum, a silent, invisible shedding of energy into the void. For billions of years, this outward flow of heat was perfectly balanced by the energy flowing in the life-giving light from the sun. On average, the sun delivered about 240 watts of power to every square meter of our world's surface. Now, with that income gone, the planet is running on its savings, and the account is draining fast. The only energy still feeding the surface is a slow, almost imperceptible warmth from below. Geothermal heat. This is the ancient, residual heat from the planet's formation, slowly leaking from its molten core and radioactive mantle. But this leak is a mere trickle. On average, it provides only about 0.09 watts per square meter. Compare that to the sun's 240 watts. The ratio is stark, a whisper against a roar. The planet is losing heat far, far faster than it can replace it. As our world cools, it desperately seeks a new equilibrium. A new point of balance where the heat it radiates into space finally equals the tiny amount of heat it gains from its own interior. Physics tells us where that new balance point lies. The final temperature, if we were to wait for millennia, would be a staggering -238°C, or just 35 degrees above absolute zero. If we waited long enough, the entire surface of our world would sink toward that profound, ultimate deep freeze. But this catastrophe would not happen everywhere, and not all at once. The Earth has a certain thermal inertia. Its vast oceans, its deep soils, the concrete jungles of its cities, and the sprawling biomass of its forests all hold on to heat. The cooling would begin at the surface, a delicate frost on the planet's outer skin, which would then deepen over time. Water, with its famously high heat capacity, becomes our most important buffer, buying us precious time. It resists the change, a vast, liquid battery slowly discharging its stored warmth. The transformation would begin at the edges. Lakes, no longer stirred by wind or warmed by the sun, would quickly freeze over, a layer of ice thickening day by day. Rivers would slow, their currents becoming sluggish as ice crystals choked their flow. Across the globe, the sea ice at the poles would bloom, expanding outward, reclaiming vast swaths of open ocean. The oceans themselves would begin to cool from the top down, a lid of ice forming and spreading, locking away the warmer waters below. As the surface temperature plummets, The very air changes. The atmosphere dries out as water vapor. The most potent greenhouse gas freezes and falls as a fine, crystalline dust. The sky, already dark, would become even clearer. The stars shining with an unwavering, crystalline brilliance. And as the light fades and the cold deepens, the very foundation of our world's biology begins to crumble. The intricate engine of life, powered by light, sputters to a halt. Because, with the sun gone, photosynthesis stops. The world takes a breath, but it is not one of relief. It is a held breath, a pause before a great plunge. When the sun vanishes, the first to feel its absence are the quietest among us. The plants. We often think of them as drinking water, but their true sustenance is light. Photosynthesis, the miraculous process that turns photons into life, stops the very instant the sunlight does. It's a switch being flipped across an entire planet. On land, the larger plants, the trees and shrubs and grasses, have a brief buffer. Their leaves continue their complex chemical housekeeping for a few hours, running on sugars stored during the last moments of daylight. It's a final burst of activity, a memory of the sun's energy still humming within their but it's a finite resource. In the vast, open oceans, a similar story unfolds. Trillions of phytoplankton, the microscopic, floating plants that form the foundation of marine ecosystems, coast on their own tiny reserves for a little while longer. But without a fresh supply of photons streaming from the sky, growth, the very engine of life, grinds to a halt. The green pulse of the planet fades. This sudden halt isn't an immediate, catastrophic death for every plant. Nature is resilient and has ancient strategies for survival. Many plants can enter a state of dormancy, a deep sleep to wait out the darkness. Seeds, protected in their hardened shells, can lie in wait for months, years, even centuries, for the right conditions to return. Mighty trees, with their vast reserves, slow their metabolism to a crawl, conserving every last drop of energy. But the intricate dance of ecosystems is timed to the rhythm of the sun. The great chain of life begins to thin almost immediately. Herbivores, the plant eaters, find their once abundant buffets dwindling. Fields of grass no longer replenish themselves. Leaves, once consumed, are not replaced. As the herbivores grow hungry and their populations decline, the carnivores that hunt them face the same grim reality. The scarcity ripples upwards, link by link, through every terrestrial food chain. The silence that falls over the plant kingdom is followed by a growing, desperate quiet among the animals. In the oceans, the effect is even more profound and far-reaching. Phytoplankton are not just food. They are the primary producers that power the overwhelming majority of marine life, from the smallest krill to the largest whales. They are the planet's other lung. As they stop producing, the great oceanic conveyor belt of carbon and oxygen begins to slow. The oceans themselves hold an enormous reservoir of dissolved oxygen, and our atmosphere, for now, remains breathable. We will not run out of air in a day, or a week, or even a year, but the fundamental balance is tipped. The engine that has maintained our atmosphere for eons has been switched off, and we are now running on reserves, coasting on the momentum of a bygone era. For humanity, survival becomes a stark, mathematical problem. Beneath the domes of surviving greenhouses and under the hum of artificial lamps, we learn a new, essential unit of measurement. Photons per plant. We calculate the precise energy required to coax a single seed into a head of lettuce, a stalk of wheat into a loaf of bread. The challenge is immense. To feed billions of people using light generated from wires would require an energy infrastructure on a planetary scale, a feat far beyond our current capabilities. We can create pockets of artificial sunlight, isolated oases of green under glass. We can sustain communities, perhaps even small cities, but we cannot replace the sun for everyone, everywhere. There is a grace period, a brief window gifted to us by our own foresight and productivity. The food we have already grown and stored in refrigerated warehouses, in massive grain silos, in the canned goods on our pantry shelves, sustains us. The fish in the sea, while no longer replenishing at the same rate, provide a temporary bounty. This global order can last for months, perhaps even longer if managed with extreme care. But the clock is ticking. The schedule's tight. Every meal consumed is a resource that cannot be easily replaced. The question that now hangs over every human endeavor is one of staggering scale. What tools do we possess, and how much energy would we truly need to artificially replicate the life-giving power of a star? What is the cost, in joules and watts, of starlight? Let's make the invisible visible. To grow crops at a massive scale indoors, we need to replicate the sun. This isn't about a gentle glow. It's about providing light equivalent to strong, direct daylight. We're talking about a flood of photosynthetically useful photons, somewhere between 200 and 1,000 watts for every single square meter. This is the same energy that leaves have been bathing in every single day, for free, for millions of years. Now, let's put that into perspective. Imagine feeding just one person. A small, personal plot to grow a variety of vegetables and staple crops might need tens of square meters of lit area. Now, take that number and multiply it by billions of people. The power required skyrockets into the tens of trillions of watts. That's a figure many times larger than our entire current global electricity consumption. It's a staggering challenge, a demand for energy on a scale humanity has never before contemplated. Where would all this power come from? Fortunately, we aren't starting from scratch. We have powerful tools in our arsenal. Nuclear fission, with its immense energy density, becomes a cornerstone. Geothermal energy, tapping into the planet's own inner heat, offers a constant, reliable source. There'll be some wind power left, at least for a while, as long as the atmosphere continues its slow, final dance. We'd rely on stored fuels and massive battery installations to buffer the system. Solar panels, ironically, become useless relics without their star. Hydropower will continue to generate electricity until the great rivers of the world freeze solid. The grid, or what's left of it, could be kept alive in pockets of civilization where fuel and reactors are available. But in this new world, energy is the most precious commodity. Every single kilowatt-hour becomes a rationed sunrise, a carefully measured dose of life-giving light. Compared to light, providing heat is the easier part of the equation. Keeping shelters and habitats warm requires significantly less power than growing food for billions. So, we prioritize. We build underground cities, burrowing deep to take advantage of geothermal hotspots. We construct vast, nuclear-powered agrarium-stowering vertical farms where crops grow in stacked layers, illuminated by hyper-efficient LEDs, designed to emit the perfect spectrum of light for photosynthesis. We would also develop algae. These are essentially living factories that turn raw electricity directly into calories, proteins, and oils, offering a highly efficient path from watts to food. In these closed systems, nothing is wasted. Every molecule of water, every gram of nutrient, is meticulously recovered and recycled. It's the ultimate closed-loop system, born of absolute necessity. Is this a solution we could implement across the entire globe tomorrow? No. It's not. But it is a foothold. It's a blueprint for survival, a way to maintain a flicker of life in the encroaching darkness. With enough advanced planning and resource allocation, these systems could be scaled. Biology, when we design its environment with precision and care, can be remarkably efficient. We can engineer our way to a new kind of harvest. And while humanity turns inward, focusing its remaining energy on these citadels of light and life, the world outside continues its transformation. The oceans, vast and deep, are beginning to change in ways we are only starting to understand. Next, the ice comes. Without the sun's warmth, the oceans begin a slow, silent transformation. At first, it's subtle. Thin, crystalline sheets of ice, like delicate panes of glass, form on the water's surface. Under the cold, distant starlight, they sparkle. A fleeting, fragile beauty. But this is just the beginning. These thin sheets thicken. They collide, raft one upon another, and weld together into vast, solid plates. Within weeks, then months, the northern bays and the marginal seas, once teeming with movement, lock up, frozen solid. The relentless cold continues its work. In a year, perhaps two, most of the ocean's surface would be encased in ice. the planet's great liquid heart would be hidden from view, especially in the vast stretches far from any geothermal warmth or the faint, lingering memory of currents. The world is becoming a sphere of ice, but ice, in its cold embrace, holds a paradox. It is both a coat and a roof. While the surface freezes solid, the water below is granted a reprieve. This is because water is a strange and wonderful substance. Unlike most materials that become densest at their freezing point, water is densest at about 4 degrees Celsius. So, as the surface water cools, freezes, and expands, the slightly warmer, denser water sinks, creating a stable, insulated layer below. The thickening lid of ice above acts like a blanket, trapping the planet's own internal warmth. Heat, a remnant of Earth's formation, constantly seeps upward from the seafloor. It rises from the great mid-ocean ridges, the volcanic seams that stitch the planet's crust together, and from hot spots deep within the mantle. This geothermal warmth, unable to escape through the insulating cap of ice, is trapped. It gently warms the deep, keeping vast volumes of the ocean liquid. This hidden liquid world could persist not just for thousands of years, but potentially for millions. On the continents, the change is just as profound. The great rivers that once carved canyons and carried sediment to the sea begin to slow. Their currents weaken as ice forms, first along the banks, then creeping inward, until finally they stop altogether, frozen arteries in a frozen landscape. The atmosphere, now brutally cold, can hold little moisture. Snow falls less and less, but what does fall is permanent. It accumulates, year after year, century after century. Glaciers, born in the high mountains, begin their inexorable creep outward. Great rivers of ice flowing in super slow motion, grinding continents beneath their immense weight. The world quiets. The roar of the surf, the rush of the river, the whisper of the wind through treesole, are silenced beneath a blanket of ice and snow. But even in this profound, globe-spanning darkness, life finds a way. Under the new, permanent polar night that now covers the entire planet, flickers of light can still be seen in the deep water. Not sunlight, but life light. Bioluminescence. A silent, secret language spoken by creatures of the abyss. For some ecosystems, the loss of the sun is irrelevant. They are the ones that never used its light in the first place. Deep on the seafloor, far from the frozen surface, are oases of warmth and chemistry. Hydrothermal vents, like smoking chimneys on a volcanic plain, spews superheated, mineral-rich water into the crushing blackness. These are the black smokers and white smokers of our own world. As deep oceans, they are portals to the planet's molten heart. Here, an entirely different kind of life thrives. Instead of photosynthesis, the foundation of this food web is chemosynthesis. Bacteria, ancient and resilient, harness the chemical energy from the vents, turning hydrogen sulfide and other minerals into food. They are the primary producers in a world without light. And around these vents, a bizarre and beautiful community of creatures float. Tube worms with bright red plumes, ghostly white crabs, and strange, pale fish all live in a tight cluster, thriving on the heat from Earth's core and the chemical feast provided by the bacteria. Their existence is a testament to life's tenacity. They prove that the engine of life doesn't have to be a star. If not the sun, then the Earth itself can provide the energy needed to sustain a world. And in this dark, frozen future, it is the planet's own inner fire that keeps the embers of life glowing. Imagine a city without a sun, its streets and towers lit not by stars or electric lights, but by the shimmering blue fires of chemistry. This is a hydrothermal vent ecosystem, a metropolis thriving in the crushing dark of the deep ocean. Here, life doesn't look up to the sky for energy. Instead, it draws its power from the very heart of the Earth. Bacteria, the true architects of this world, perform a kind of magic. They take the chemical energy bubbling up from the planet's interior compounds like hydrogen sulfidon, use it to build sugars. This process, called chemosynthesis, is the foundation of everything. It's the equivalent of photosynthesis, but fueled by volcanic heat instead of sunlight. Upon this chemical foundation, a strange and wonderful community arises. Giant tube worms, some taller than a person, wave their blood-red plumes in the warm, mineral-rich water. Blind white shrimp swarm over the volcanic chimneys, and crabs scuttle across the seafloor, their shells like porcelain in the dark. These vent fields are like oases, scattered along the vast, underwater mountain ranges known as the global ocean ridges. They aren't everywhere, but where they exist, they are lifelines. Hotspots of incredible biodiversity in an otherwise sparse landscape. But even away from these bustling chemical cities, life persists. We are now discovering a vast and ancient deep biosphere, a hidden kingdom of microbes that permeates the very rock beneath the ocean floor. They live in tiny pores and fractures in the crust, extending 4 kilometers below the surface. Their existence is one of extreme patience. They live incredibly slowly, metabolizing trace amounts of energy trickling up from the planet's core. For these organisms, time moves differently. They have endured for eons, completely unaware of the cycle of day and night, of seasons, or of the sun that bathes the surface world in light. In a world without our star, this quiet, hidden realm would not just be a curiosity. It would become the planet's dominant form of life, a silent, global network of survivors. And this deep life isn't confined to the oceans. On land, beneath our feet, Earth's crust also harbors its own hidden ecosystems. Groundwater aquifers, vast underground seas and rivers, are not sterile. They support complex microbial communities. Deep within rock fractures, life finds a way, led by slow, subtle chemical reactions between water and minerals. Warmth seeps up from below, providing just enough energy. For these inhabitants, darkness is the norm. They are the original masters of living without light, their entire biology tuned to a world of pressure, rock, and chemical whispers. They show us that life is not merely a thin film on the planet's surface. It is woven into the very fabric of the world itself, a resilient force that occupies every conceivable niche, no matter how extreme or how far from the sun's reach. There are profound lessons for humanity in these deep, dark worlds. These organisms are masters of efficiency. They live in closed loops, where every waste product is a resource for something else. They demonstrate perfect recycling, a concept we on the surface are only just beginning to grasp. They eat at the very base of the energy pyramid, converting raw chemical potential directly into life. We can learn to emulate their strategies. In a future without a sun, we could harvest heat from geothermal wells, tapping into the same planetary furnace that powers the vents. We could use this energy to generate electricity, creating artificial light to grow food in vast, subterranean farms. We could cultivate specialized bacteria, much like those in the deep, that can turn simple gases into protein and fat, creating nourishment from the air itself. It might not seem romantic, building a civilization based on geothermal heat and microbial chemistry, but it would be robust. It would be a life anchored to the enduring energy of the planet, not the fleeting grace of a distant star. And as life below adapts and endures, the air far above us would be changing too. Without the constant churn of photosynthesis and respiration driven by sunlight, the atmosphere would begin a slow, delicate transformation. The familiar balance of gases we breathe, the very character of our sky, would start to shift. Its composition, once held in a dynamic equilibrium by surface life, would begin a quiet and inexorable fall toward a new state. Next, we will explore the atmosphere's quiet fall. As the last echoes of warmth retreat from Earth's surface, a profound change begins in the sky above. Water vapor, the planet's most abundant greenhouse gas, can no longer remain suspended. It condenses, falling as a final, planet-wide snow. The clouds that once blanketed our world thin out, becoming wispy and ghost-like. This celestial blanket, which for eons trapped the sun's heat, now becomes lighter, more porous. With its thinning, the remaining warmth escapes into the void of space at an ever-increasing rate. This feedback loop is relentless. The colder it gets, the faster the heat leaves. And the faster the heat leaves, the colder it becomes. The planet is caught in a spiral of accelerating cold. Years stretch into decades. The surface temperature plummets, 2 levels unimaginable in our time. Now, the very air we once breathed faces a transformation it has never known. Oxygen and nitrogen, The fundamental components of our atmosphere approach a critical threshold. At the standard atmospheric pressure we were used to, oxygen begins to liquefy around -183 degrees Celsius. Nitrogen, even more resilient, surrenders to the cold near -196 Celsius. The surface of the Earth will eventually become colder than that. Imagine standing on a silent, frozen plain. As the temperature drops further, the air itself begins to condense. It might first appear as a strange, ethereal frost settling on the ground, a delicate lacework of frozen gas. Into lowest, most sheltered valleys and basins, this condensed air could begin to pool. You might see pale, blue liquids shimmering faintly under the starlight, liquid oxygen sloshing gently before freezing solid into brittle, glassy sheets. Nitrogen would follow, forming its own colorless, frozen lakes. This atmospheric collapse won't be uniform or instantaneous. The planet still has a pulse, a deep, geothermal warmth bleeding from its core. Volcanically active regions, geothermal hotspots, and vast reservoirs of buried heat will keep many places comparatively warmer for centuries, even millennia. These oases of residual warmth will resist the freezing of the air, creating localized pockets where a thicker atmosphere might persist for a time. But viewed from a global perspective, the trend is undeniable. The atmosphere will progressively thin as its constituent gases settle out, freezing onto the surface. Consequently, the atmospheric pressure will drop dramatically. Long before the air freezes, the extreme cold would make breathing outside without aid impossible. But eventually, a new, more fundamental problem would arise. There simply wouldn't be enough gas left overhead. The sky would literally be falling, not as a cataclysm, but as a slow, silent settling. The pressure would become too low to support human life, the air too thin to fill our lungs, even if we could somehow withstand the cold. Yet, even in this state of profound cryogenesis, Earth is not a dead, inert marble. Beneath the mile-thick roofs of ice that now covered the oceans, a world still circulates. The planet's internal heat engine continues to churn, driving currents in the subglacial oceans, a hidden biosphere breathing in its own unique way. The heart of the Earth still beats, albeit faintly, under a frozen shell. But as we contemplate this dark, icy world, a question hangs in the star-dusted sky. What of our constant companion, the moon? Its gentle light was always just a reflection of the sun. Now, without sunlight to illuminate its face, does it still hold any sway over our frozen planet? Does the moon still matter in this endless night? The sun may have vanished from our sky, but its absence does not sever our oldest cosmic connection. The moon, our silent, steadfast companion, continues to exert its influence, its gravitational hand still reaching across the void to stir our world. The tides, that ancient, rhythmic breath of the oceans, persist. They are different now, of course. Simpler, more predictable. Before, the sun's own immense gravity played a crucial role in this planetary dance. It would align with the moon to create the dramatic spring tides, their combined forces pulling the oceans high, or it would work against the moon, resulting in the gentler neap tides. This celestial tug-of-war created a complex and ever-shifting pattern. Now, with the sun's gravitational voice silenced, the lunar tide is all that remains. The rhythm is pure, a steady, solitary pulse. The total variation is less extreme, roughly 2/3 of what it once was, a calmer, more measured swell. The great surges that once reshaped coastlines have mellowed, but the fundamental rise and fall endures, a testament to the moon's unwavering grip. Even beneath the miles-thick blanket of ice that now encases our planet, this tidal force is not idle. It doesn't stir open water, but it flexes the entire ice shell of the global ocean. Imagine a slow, planetary scale inhalation and exhalation. This constant, subtle movement creates immense stress within the ice. Great fissures and cracks appear, running for hundreds of miles, only to slowly grind shut and freeze over again. This process, this cracking and healing of the world's frozen skin, is not just a surface phenomenon. It has profound implications for the dark ocean below. The movement helps to drive circulation, preventing the abyssal waters from becoming completely stagnant. It stirs the deep, mixing nutrients and heat that well up from geothermal vents on the seafloor. For any life that might huddle near these oases of warmth, this tidal mixing could be a lifeline. It circulates essential elements, and perhaps even helps disperse organisms, preventing complete isolation. Even in the smaller, landlocked seas and vast subterranean lakes, the faint lunar pull prevents the water from settling into absolute stillness, a subtle but vital agitation in the unending dark. And what of the moon itself? Once a beacon in our night, a canvas for sunlight, it has become a ghost. We used to see it illuminated by the sun, its phases, a familiar celestial clock. When it was a sliver in the sky, its dark side was often faintly visible, lit by the gentle glow of earth-shine sunlight reflecting off our own planet as clouds and oceans. But with the earth now dark and frozen, that secondary light is gone too. The moon is now a profoundly dark object, a sphere of black rock against a black star-dusted curtain. It is a void in the star field. Occasionally, perhaps, a glimmer might betray its presence. The combined light from distant stars, though incredibly faint, could catch its edge at just the right angle, creating a whisper-thin, silvery arc against the emptiness. But for the most part, it is an invisible partner, detectable only by the way it eclipses the stars that pass behind it. It is a black companion on a fixed, predictable path, its orbital period unchanged. A constant in a world of radical change. For those of us who remain, this orbital period, the lunar month, has taken on a new and vital significance. Down in the deep shelters, we mark its passage. Scratches on a cavern wall, a knot in a cord, a digital counter ticking over. It is our calendar, our last reliable clock. The slow, predictable cycle from one new moon to the next offers a way to measure time, to structure our existence in the endless night. The moon, dark and unseen, still governs our sense of time's flow. Its enduring rhythm raises a larger question, one that echoes in the silent depths of our new reality. Just as the moon continues its faithful orbit around us, we and the moon together are on a much grander and far more uncertain journey. Our planet is no longer tethered to a star. We have slipped our gravitational leash and are now drifting, untethered, through the interstellar medium. Our solar system is a memory. A new, unknown path lies before us, a trajectory into the vast, cold darkness between the stars. We are a rogue planet, a ship cast away on the cosmic ocean. Where are we going? What destiny awaits our wandering world in the infinite expanse? That is the next chapter of our story, the journey into the endless dark. Even with the sun gone, our motion doesn't cease. It never could. Earth has always been in a state of perpetual movement, a cosmic dance. We spun on our axis. We orbited the sun, and together with the sun, we journeyed around the vast, spiraling arms of the Milky Way galaxy. Now, freed from the sun's immense gravitational pull, we simply continue. We inherit the momentum we already possessed at the moment of our release. Imagine being on a carousel that suddenly disappears. You would fly off in a straight line, following the path you were on at that exact instant. That's our fate. We sail forward, a solitary vessel, at a speed of roughly 30 kilometers per second. This is the velocity we once used to orbit our star, and now it propels us along a tangent, a straight line extending from our old, circular path. But that's not the whole story. We also carry with us the sun's own galactic speed. Our star was never stationary. It was hurtling through the galaxy at tens of kilometers per second, tracing a grand, sweeping curve around the galactic center. Since we were bound to it, we shared in that velocity. In practice, our new trajectory is a combination of these two motions. We are essentially continuing along the sun's former galactic path, a straight-line inheritance from a journey we started together billions of years ago. You might imagine us drifting aimlessly toward the nearest star, like a ship spotting a distant lighthouse. But space, and its profound emptiness, doesn't work that way. The distances are simply too staggering to comprehend. Proxima Centauri, our closest stellar neighbor, is over for light years away. At our current speed, a journey there would take tens of thousands of years. Our path isn't aimed at it, or at anything in particular. We are simply moving. With the sun gone, its role as the gravitational shepherd of our solar system has ended. The cosmic family has disbanded. The planets, asteroids, and comets that once danced in predictable orbits are now, like us, set free. We scatter like seeds from a burst pod, each on its own independent trajectory, spreading out into the interstellar void. Most of our former neighbors are too distant and too dim to be seen with the naked eye. We are alone, but we are not the only ones on this new, unguided voyage. Looking up from the surface of this wandering Earth, you wouldn't be able to tell that anything has changed. The constellations would appear exactly as they always have. The stars are so incredibly far away that their apparent movement, their parallax, is imperceptible across a human lifetime. It would take centuries, even millennia, for their positions to shift in any noticeable way. Our grand journey is invisible to the casual observer. The night sky offers a false sense of stillness, a beautiful lie. But our instruments would tell a different story. They would detect no yearly wobble in the star's positions, the telltale sign of a planet orbiting a sun. Our radio telescopes would hear only the cold hiss of the cosmos, no familiar broadcasts from a parent star. We are now a rogue planet, a wanderer, not a member of a solar family, but a solitary entity. There's a strange, pure, and perhaps lonely status in this new identity. We are defined not by what we orbit, but simply by what we are. There is a subtle, almost philosophical comfort in this new reality. Our speed is constant. Our path is a straight line through the silent vacuum of space. There is no acceleration, no external force pushing or pulling us. It's the purest form of motion described by Newton's first law, a state of perpetual, unchanging travel. The cosmos, however, is not entirely still. It's a dynamic environment, filled with currents of gas, wandering stars, and immense clouds of dust. Over the vast timescales that now define our existence, encounters are not just possible, they are inevitable. Our straight line will eventually cross the path of something else. The question that hangs in the silent darkness is, what will that be? And would we ever, in the distant eons to come, feel the gentle, guiding touch of another star's gravity again? Our journey continues, and as we sail on, we must consider the possibilities that lie ahead, passing suns and the rare chances they might offer. The vast emptiness of space is not entirely empty. Stars, like celestial nomads, drift through the galaxy. They form clusters, te dispersi, and sometimes, en terre longue. Slow journeys their paths intersect. A stellar encounter, a close approach between two stars, is not a question of if, but when. Yet, the when is everything. The odds that our wandering Earth, now a rogue planet, would pass close enough to another star to be captured into a new orbit are astronomically small, at least on a timescale that we can comprehend. It's a cosmic lottery ticket with staggering odds. Such an event might happen, but it could take tens of millions, or even hundreds of millions of years. This is a span of time so immense that our civilizations, our history, our very species would be but a fleeting moment in its wake. The long wait in the dark continues. Even if a star were to wander into our cosmic neighborhood, a successful capture is far from guaranteed. It's a delicate gravitational ballet, a dance requiring an almost impossible precision. The approaching star would need to have just the right mass, approach at the perfect speed, and from the exact right angle. It's like trying to thread a needle from a light year away. A slight deviation in any of these factors, and the outcome changes dramatically. The more probable result wouldn't be capture, but a slight gravitational nudge. Our path through the galaxy would be altered, deflected just a little, before we continued on our solitary voyage. We would be a cosmic billiard ball, caromed off a stellar cushion, but still rolling into the darkness. We are not easily caught, but while we journey, our position within the grand structure of the Milky Way remains. We are still adrift within its sprawling spiral arms, a part of its immense, rotating disk. The night sky, our constant companion, is therefore an ever-present spectacle. The faint, ghostly glow of the zodiacal light, that haze of dust once illuminated by our sun, is long gone. In its place, however, The galaxy's band is a steady, brilliant river of light, a celestial torrent of stars, nebulae, and dust lanes stretching from one horizon to the other, and with our atmosphere growing thinner, clearer, free from the distorting effects of a parent star's light. The view is breathtaking. You can trace the intricate structures, the dark rifts, the glowing clouds of gas where new stars are being born. The clarity is unparalleled, even as you shiver under layers of heavy insulation, gazing up at a beauty born from profound loss. The cosmic dance isn't limited to stars alone. Not all encounters are so dramatic. The space between stars is filled with wanderers of a smaller scale, clouds of interstellar dust and countless tiny meteoroids, remnants of cosmic creation and destruction. Without the sun's constant outward push, its radiation pressure and the powerful solar wind that once swept our system cleaned, the behavior of this material subtly changes around us. These are small adjustments in the grand scheme of things, but our new existence is defined by such subtleties. The sky is full of them now, a delicate and ever-changing tapestry of faint light and shadow, of tiny, fleeting streaks as micrometeoroids burn up in what remains of our upper atmosphere. Each one is a small reminder that we are not entirely alone in the void. In the face of these immense cosmic timescales and celestial mechanics, the immediate focus shifts. The distant hope of a new sun is too far away to be a practical concern. The most pressing questions are not written in the stars, but here, on the surface of our dark world. It's not the distant stellar encounters that matter most right now. It's us. It's the immediate challenge of survival. Oh, humans, a species born of light and warmth, adapt and reshape an entire planet for an existence in the long, unending dark. The ultimate engineering project has begun, driven not by ambition, but by the simple, powerful instinct to endure. The solutions must be found not in the sky above, but in the ground beneath our feet. When the dust settled and the sky went dark, survival became a design problem. Our species, once masters of the surface, now had to look down, deep into the earth, for warmth. The first and most critical challenge was heat. In a world rapidly turning to ice, we sought out the planet's inner fire. Geothermal fields, places like those in Iceland, New Zealand, and the Great Rift Valley became the new capitals of human civilization. These weren't cities of glass and steel reaching for a sun that no longer warmed us. They were cities that descended. We began to carve our homes directly into the Earth's crust, creating vast, warm caverns in the solid embrace of basalt and granite. It was an architecture of necessity, an inversion of everything we had built before. Our habitats were wrapped in shells of vacuum insulation, a technology perfected for space now repurposed to keep the encroaching cold at bay. Tunnels, the new streets of our subterranean world, were lined with pipes carrying hot water, a constant flow pulled from wells that tapped into the planet's molten heart. Every corridor pulsed with a gentle warmth, a lifeblood of heated water circulating through the rock. Nuclear reactors, once a source of debate, became pillars of our survival. Managed with meticulous care, they provided not only electricity for our dark world but also an abundance of heat. Their waste heat, once a problem to be discarded into rivers and oceans, was now a resource too precious to lose. We engineered systems to capture every last joule, using it to maintain the delicate temperature gradients that drove air circulation within our sealed environments. In this new world, efficiency wasn't just a goal, it was beautiful. Every watt counted. Every degree of warmth was a victory against the endless cold. With warmth secured, the next challenge was food. The sunlit fields of the past were gone, so we built new ones, stacked vertically in our underground caverns. Under the purple and pink glow of leads, we converted electrons directly into calories. This forced a fundamental redesign of our diet. We turned to nutrient-dense crops and microbes that thrived in low light. Our new staples were mushrooms, cultivated in sprawling fungal farms, duckweed and spirulina, grown in illuminated vats, and even bacterial protein, synthesized from hydrogen, nitrogen, and carbon dioxide harvested from the air. Animal agriculture, a hallmark of the old world, shrank dramatically. The immense energy required to heat large enclosures meant that only small, carefully managed pockets could be sustained. Every gram of fertilizer, every nutrient, was meticulously recycled in closed-loop systems. Nothing could be wasted. Water, too, became part of this closed cycle. Condensers on ventilation systems harvested the moisture from every breath, every wisp of steam. Our biospheres were engineered to tolerate almost no leaks, each one a sealed testament to our ingenuity. And on the surface, beneath the thick, protective roof of ice that now covered the oceans, a new kind of vessel emerged. Ships, vast and slow-moving, became mobile communities, crawling across the dark, frozen seas to connect the scattered subterranean cities. Day-weary arcs, not against a flood, but against a deep, unyielding freeze, their hulls insulated against the brutal cold above. All of this, the geothermal cities, the stacked farms, the closed-loop systems, took time to build. We had a grace period of months, perhaps a few years, before the harshest cold of the long night settled in permanently. The initial shock gave way to a focused, determined effort of engineering and construction on a scale never before imagined. It was a race against the thermometer, a global project to burrow and build before the surface became entirely uninhabitable. As our new world took shape in the warmth of the deep earth, a fundamental choice began to loom, a question that hung in the recycled air of our caverns. We had secured a foothold, a place to survive. But was this to be our permanent home? Do we stay put, sheltering under the ice, or do we sail away? What if the sun just ... vanished? We've explored the immediate aftermath, the minute delay, the plunge into eternal darkness, and a deep, world-altering cold. We've talked about surviving on a frozen Earth, huddling around the planet's own geothermal warmth, but humanity has always looked to the stars. Without our star, is there any reason to look out into the void anymore? What good is space without a sun? Surprisingly, the answer isn't a simple none. Some places in our former solar system still offer a flicker of energy. The gas giants, Jupiter and Saturn, are not just colossal balls of gas. They are celestial furnaces in their own right. They radiate more heat than they receive from the sun, or, in our scenario, than the asterisk used. This internal heat comes from a slow gravitational contraction, a process known as the Kelvin-Helmholtz mechanism. It's a faint warmth, certainly not enough to heat a rogue planet like Earth from afar. But for their own moons, it's a different story. Think of moons like Europa, orbiting Jupiter, or Enceladus, circling Saturn. These worlds were already fascinating prospects for life because of their subsurface oceans, kept liquid not by sunlight, but by the relentless pull of their parent planets. This gravitational tug-of-war creates tidal forces, flexing and kneading the moon's interiors, generating immense frictional heat. Add to that the gentle, persistent warmth radiating from Jupiter or Saturn, and these ice-covered moons become some of the most appealing destinations in the dark. They already have vast, hidden oceans. Their hypothetical inhabitants would already be experts at living under a thick crust of ice, completely independent of a star's light. For a humanity desperate for a new home, they might seem like oases in the cosmic desert. However, the dream of reaching these oases is a brutal one. The journey itself presents an almost insurmountable challenge. Our conventional methods of space travel are now obsolete. Solar-powered spacecraft, the workhorses of modern exploration, are nothing more than useless sculptures in a sunless void. The only viable option becomes nuclear propulsion. We would need to harness the power of the atom to generate the immense energy required for such a voyage, not just for propulsion, but to keep the crew and systems from freezing solid in the absolute cold of interplanetary space. The greatest obstacles are time and energy. Mars, once our most likely second home, is now colder than ever. A silent, frozen desert with little to offer. The outer planets and their promising moons are unimaginably far, and we must remember a crucial, devastating fact. When the sun vanished, its gravitational leash on the solar system snapped. Every planet, every moon, every asteroid was flung into its own trajectory, racing away from its former orbit on a straight path into the interstellar dark. We aren't just trying to reach a distant destination. We're trying to catch a series of moving targets that are actively speeding away from us, and from each other. The calculations would be staggering. The fuel requirements, astronomical. Faced with this reality, the wisest course of action might be to look not outward, but inward. Closer to home, our most reliable, accessible, and powerful source of heat remains Earth itself. The geothermal energy bleeding from our planet's core is local, constant, and immense. It powered the first stages of our survival in this sunless world, and it could sustain us for geological ages. Perhaps the grand human adventure isn't about chasing fleeting warmth across the void. Perhaps it's about burrowing deep, harnessing the power beneath our feet, and transforming our own rogue planet into a self-sustaining fortress against the cold. Staying put might be far wiser than chasing ghosts in the dark. But whether we stay or go, this thought experiment opens a door to another, even more profound question about the nature of the universe. We've been operating under the assumption that the sun simply vanished, an event that violates the laws of physics as we know them. So, let's change the scenario slightly to one that is physically plausible, though no less terrifying. What if, instead of disappearing, the sun had used up its fuel and collapsed under its own gravity, becoming a black hole of the exact same mass? What would that mean for Earth and the now-chained solar system? The darkness would still come, but the story would be very, very different. Let's begin a thought experiment, nestled inside the larger one we've been exploring. Imagine, just for a moment, that our sun, in an instant, didn't vanish. Instead, it collapsed into a black hole of the exact same mass. What would happen to Earth? What would happen to us? The immediate, intuitive answer is that we'd be sucked in, a catastrophic spiral into an abyss. But the universe, as it so often does, holds a surprise. In terms of gravity, almost nothing would change. Earth's orbit would continue, serene and undisturbed. We would be pulled in because the gravitational force exerted by an object depends on its mass and your distance from it. As long as the black hole has the same mass as the sun, and we remain at our comfortable 93 million mile distance, the pull would be identical. We would simply continue our annual journey, circling an invisible, silent partner where a star once blazed. Of course, the most profound change would be the loss of light. Daylight would vanish instantly, plunging our world into a perpetual night. The life-giving warmth would cease, and the planet would begin a long, slow freeze. But our cosmic dance would persist. We wouldn't be flung into the void. We'd be locked in a faithful orbit around a point of pure darkness. The gravitational anchor would hold firm, even as the light went out. This is a crucial distinction from the scenario we've been investigating in our main story. In our narrative, the sun doesn't just transform, it disappears entirely. Both its light and its immense gravitational influence are removed from the fabric of space. The tether is cut. That's why, in our version of the story, Earth doesn't continue to orbit anything. It flies off in a straight line, a tangent into the cold, interstellar dark. We chose this more severe path because it forces us to confront the raw fundamentals of heat, survival, and the very nature of time itself. Let's return to the black hole sun for a moment, though. What would that sky look like? It would be a breathtaking, if terrifying, sight. With the sun's glare gone, the daytime sky would be filled with the brilliant, sharp points of distant stars, a celestial tapestry usually reserved for the clearest nights. And at the center of it all, where our familiar star used to be, would be a small, perfect circle of absolute black. This wouldn't just be an empty spot. However, it would be an active participant in the visual field. The immense gravity of this tiny point would bend the light from the stars behind it, a phenomenon known as gravitational lensing. We would see a faint, ghostly ring of warped starlight encircling the Voigt Einstein ring, a cosmic halo around a ghost. It would be a stark, beautiful, and deeply unsettling monument to what we had lost, the sun's ghost, still shaping the light around it. But again, our journey is different. We are on a world cast adrift, without even that gravitational ghost to hold on to. We are traveling a straight line through an ever-deepening cold. We've spoken about the fading warmth of the Earth, the eventual freezing of the oceans, and the pinprick guidance of the stars. We've seen how the moon continues to offer its reflected, second-hand glow for a time. But in this profound and spreading darkness, there is one more source of light. A subtle, ancient, and beautiful glow we haven't yet discussed. It isn't starlight, which comes from suns, much like our own. And it isn't moonlight, which is merely a reflection. This is something else entirely, something far, far older than both. It is the first light, a relic from the very dawn of creation. Even with our star gone, a profound stillness settling over the planet, Earth is not cast into absolute darkness. There is still light, though not as we've ever known it. Across the entire sky, in every direction, there is a faint, perfectly uniform glow. This isn't starlight, nor is it the last vestige of our sun. This is the cosmic microwave background, the oldest light in the universe. It is the afterglow of creation itself, the faint, residual heat left over from the Big Bang. Imagine the universe beginning as an infinitesimally small, incredibly hot, and dense point. As it expanded, it cooled. The light from that initial, fiery state has been traveling across space for nearly 14 billion years. Over that immense journey, the expansion of space has stretched its wavelength, shifting it from brilliant, visible light into the microwave part of the spectrum. It has cooled to a mere 2.7 degrees above absolute zero, just 2.7 Kelvin. You cannot see it with your eyes. Toharu senses. It is an absence, a total blackness, but two sensitive instruments. It is an omnipresent hum, a whisper of heat from the universe's infancy, compared to the deepening cold of our wandering Earth. 2.7 Kelvin might seem like a touch of warmth. However, the energy this signal carries is unimaginably weak, far too feeble to warm our frozen world. It is not a source of heat for us, but a constant, a backdrop. It is a profound reminder that we are not adrift in an empty void, but floating within something vast, ancient, and filled with a history that predates our sun, our planet, our very atoms. And this ancient glow is not the only light that remains. In the upper reaches of our atmosphere, a delicate phenomenon called airglow persists. Chemical reactions, energized by the last traces of solar radiation and cosmic rays, cause atoms and molecules to emit a faint, ethereal light. It's a planetary aurora, a soft, diffuse luminescence that paints the high sky in subtle, shifting veils of green and red, a ghost of the atmospheric dynamics that once were. Then there are the transient visitors, meteors, tiny grains of dust from long-dead comets and shattered asteroids, still streak across the upper atmosphere. For a brilliant, fleeting moment, they burn up, drawing a fiery line against the permanent night, a brief, startling reminder of the cosmic debris field we travel through. Down below, on the planet's surface, the weather systems, though slowly losing their energy, still grind against each other. Massive, slow-moving storms can unleash bursts of lightning, illuminating the frozen landscapes for a split second in a stark, silent flash. These are the planet's own fading heartbeats. And, of course, there is us. In scattered enclaves, beneath the ice or deep underground, humanity clings on. Where we persist, there is artificial light, a soft glow from a hydroponic bay, the focused beam of a headlamp in a tunnel, the shimmering of a protected habitat seen from a distance. Each point of light is a testament to resilience, a declaration that we are still here, still thinking, still working, still hoping. This unending night, once a terrifying prospect, has offered an unexpected gift. Without the sun's overwhelming glare and atmospheric interference, our view of the cosmos is clearer than it has ever been. On the dark, silent surface, our radio telescopes listen with a newfound clarity. We can map the vast, swirling clouds of neutral hydrogen that trace the spiral arms of our own Milky Way galaxy. We can listen to the clockwork ticking of pulsars, the superdense remnants of massive stars using their precise rhythms to test the fabric of space-time itself. We can peer deeper into the dark, searching for signals from far, far away, listening for whispers that might tell us we are not, and have never been, alone in this vast expanse. The science we can do now is breathtaking, a new golden age of astronomy born from our darkest hour. We are unraveling the universe's secrets under a perfect, permanent night sky. And yet, amidst the data, the discoveries, and the quiet awe of the cosmos laid bare, Another question begins to form. It is a question that has been lingering in the background. A question we have, perhaps, saved for last. Because it is the most difficult one of all. With the fire of our sun extinguished, and the cold creeping ever deeper into the heart of our world, what is the fire we now carry within ourselves? What story do we tell ourselves to keep going? In the profound hush of a sunless world, warmth has become a new kind of language. It is information, a currency of survival and connection. A hearth's gentle glow, shimmering against ice-hewn walls, no longer just means heat. It signifies a community, a gathering of souls against the endless night. A faint, rhythmic ping from a radio receiver, cutting through the static, is a declaration. Someone else is out there, listening in the dark, just like us. Across the frozen face of our planet, human settlements, nestled deep beneath layers of ice and rock, begin to find one another. We are like fireflies in an infinite cavern, our small lights blinking in a coordinated dance. We are learning to connect, to weave a new tapestry of civilization from the threads of our shared predicament. Our geothermal hubs, the beating hearts of our subterranean cities, are being linked together into vast mesh networks. Through these digital arteries, we share more than just data. We share life itself. Precious seeds, carrying the genetic memory of a sunlit world, travel from one enclave to another. Linus of code elegant solutions to the complex problems of our new existence are exchanged and improved upon. In this world of shadow, we have rediscovered the pure essence of art. We create with light and with sound, painting ephemeral masterpieces in the dark that do not waste a single precious jewel of heat. Projections of light dance across cavern walls, telling stories without words, while melodies composed of resonant frequencies echo through our halls, a testament to a spirit that refuses to be extinguished. Our children, born into the twilight, look up at the sky, with eyes unburdened by the memory of a single, blinding star. They learn the new constellations, the intricate patterns of distant galaxies and nebulae that are now visible every single night. A celestial roadmap painted across a canvas of perfect black. Their bedtime stories are not of princesses and castles, but of the old myths of the Santalis of a great golden river that once flowed through the sky, a river from which we all used to drink. Our scientists, driven by a new kind of curiosity, have turned their attention inward and downward. They catalog the myriad forms of life that have always thrived in the deep, creatures that never knew the sun and never cared for the rhythm of day and night. They are the original inhabitants of this dark world, and they hold secrets we are only just beginning to understand. Our engineers have become modern-day alchemists, masters of transformation who turn what was once considered waste into vital resources. Every byproduct, every scrap, every exhalation is captured, repurposed, and reintegrated into the delicate cycle of our closed-loop systems. The concept of trash has become obsolete. In this world, everything has value, and our farmers, the stewards of our survival, have become biochemists. They tend to vats of glowing algae and fungi, coaxing life from carefully balanced chemical solutions, cultivating nutrient-rich harvests in vertical farms that climb the walls of our deepest shelters. They are the guardians of our sustenance, painting with a palette of minerals and microbes. And then, perhaps, on a night no different from any other, a new sound emerges from the quiet, deep within a cavernous observatory. A sensitive detector, listening to the symphony of the cosmos, hears something extraordinary. A pattern in the noise, a structured signal, clear and intentional, calling from the stars. Is it another civilization? A people long adapted to their own darkness, reaching out across the unimaginable void to say, "We are here." Or is it simply a pulsar, a cosmic lighthouse spinning in the deep, its steady rhythm a chance occurrence? It doesn't matter. We will claim it as our own. We will turn its celestial beat into a metronome for our hope, a steady pulse to guide us through the long night. But before we dare to answer that call, before we announce our own presence to the vast, silent universe, we owe ourselves a moment of quiet reflection, a closing look at our journey. In the shadow of our lost star, what profound truths have we been forced to learn about resilience, about community, about ourselves. Now, close your eyes. Picture the Earth as it is in this story. A beautiful pearl, wrapped in a delicate shell of ice, drifting silently through the vast, dark expanse of the galaxy. It's quiet, but it's not still. Underneath that frozen shell, the deep oceans still move, their currents swirling in the dark. Deep within the planet's core, rocks still hold their ancient warmth, and life still breathes. It breathes slowly, cleverly, drawing its energy from chemistry and its strength from immense patience. Through this imagined journey, we have learned a profound lesson: that sunlight is a precious gift, a wonderful source of energy, but it is not the only kind of energy the universe allows. There are other ways to live, other sources of power hidden in the fabric of existence. We learn to think in different timescales, to feel the universe's many rhythms. We considered the 8 minutes it takes for light to travel from the sun to us, a tiny delay that holds immense significance. We watched, in our minds, the weeks it would take for the weather to finally wind down, for the last storms to quiet into a global calm. We imagined the years passing as the oceans sealed themselves over with a thick, protective layer of ice, and we contemplated the millennia of geothermal endurance, the planet's own internal heat providing a steady, reliable warmth from deep below. We learned that gravity, like light, speaks at a finite speed, its influence traveling across space. We understood that temperature is not a static thing but a delicate balance, a constant dance of energy gained and energy lost. And perhaps most importantly, we learned that life, when pressed, when faced with the ultimate challenge, can shrink down to its absolute essentials and still, in its own quiet way, sing. Most of all, we learned that we humanity are creative and resilient. We can build cities of warmth, enclosed havens that glow against the endless night. We can create farms of photons, using technology to grow food with artificial light, sustaining ourselves in the absence of the sun. We can foster cultures of care, where looking after one another becomes our most important task. We have the capacity to make a home in the night, not by trying to deny the darkness or fight against it, but by understanding it, by studying its rules, and by shaping our world gently and wisely within it. This journey has shown us our own potential for adaptation, our ability to find solutions in the face of the unimaginable. The darkness isn't an enemy to be defeated, but a new environment to be understood. So, if the sun ever did vanish, as it has in our story tonight, it would not be the end. It would be a profound change, certainly a shift in the very foundations of our world. But it would be just that, a change. A change in the kind of light we live by. We would move from the brilliant, golden light of a star to the soft, steady glow of our own ingenuity, our own compassion, and our own enduring spirit. The light of a star would be replaced by the light of humanity. If you enjoyed drifting through this calm, mysterious journey with us, and if you'd like to hear more, science told as a gentle lullaby for the curious mind, please consider subscribing to Hypnosphere. We have so many more wonders to explore together. For now, close your eyes, keep wondering, and we'll meet you again in the next night sky.